Hello and welcome back. We're coming to you from our office in the downtown, and today is window washing day, as you can see. Today's topic is a test of two means small sample. Let's begin. This is presentation 9.3. The topic is the difference in two sample means small sample, and we asked you to look in your textbook and workbook, chapter 9. We want to acknowledge the development team of Brad, Spencer, Amanda, and myself. Now we're just going to do a brief review of the 9.1, and we're looking at two populations, mean 70, standard deviation 18, and so on. If we take random samples from each of these, population X, sample size 36, they'll tend to cluster about the population mean 70, and standard error, standard deviation 3. And if we repeat that for the Y's, the second population, the sample means will cluster about 80 with standard deviation in the sample means y bar to be equal to 4. And we're saying that if you systematically take the difference of means, y bar minus x bar, they're coming on the screen now, these will be roughly normally distributed and will cluster around the difference in the two population means, which in this case is 70. And here's the key thing: the variances add. The variances are standard deviation squared. So when you take the square of the 3 and the 4 and add them up, you get 25. Square root is 5. The standard error, or standard deviation in the differences, will be equal to 5. And these add together in the sense of Pythagoras' theorem, much like the right triangle you see coming on the screen here. Now we're going to look at a particular problem here. We're looking at runoff from agricultural fields, and we're looking at chlorine levels in two lakes, and the suggestion is that the chlorine levels have significantly increased. And we have here the two random samples. Now this is the Excel output here, the mean, standard deviation, and so on. So the X bars appear at the top there, as you can see. Now these are the S squares, these are the variances, which are standard deviation squared. Now we're going to state the hypotheses. There's no significant difference in the levels, 2012, 2008, and the difference is around 0. The alternative, the chlorine levels have significantly increased, that the levels in 2012 are greater than that of 2008. And now we're going to look at the sampling distributions. In 2008, based on samples n equal 12, standard deviations, coming on the screen here now, you see this is already s squared, so we take the square root, and that is the variability in the x bars. Similarly, if we look at the similar thing in the y bars, the standard deviations will be coming on the screen there now, the square root of these two entities, and that corresponds to the variability about the population mean here. Now if we systematically take the difference in population in sample means, the difference should be around 0. That's our null hypothesis. We assume it's correct. But the variances add together. And as you can see here, the variability above the mean of the differences is 0.766, greater than either of the two. And looking at the confidence interval, and on the screen here you see the t-critical 1 tail 1.72. Note the degrees of freedom here is 21, which is somewhat controversial depending on the books you use. We're going to use the Excel output. And this means that if your t observed or t statistic exceeds 1.721, we're going to reject H0. So let's look at the evidence. The evidence is by way of the observed difference, which is the difference between these two means on the screen here, divided by the standard error, which comes from above, and that comes out to be 2.003, which appears here in the Excel output. Now we're going to, by the way, this exceeds our critical value, so we're forced to reject H0. The p-value, the probability of getting a difference greater than our observed difference when H0 is true, is 0.029. It looks like it's sufficient evidence to reject H0, and that appears here. Now, it's an unusual event. We're looking at a confidence interval now, It's the observed difference plus or minus t times your standard error. The observed difference is given up here, the difference between the x bar and y bar, and your critical value is the 2.0796. This is a two-tail value, and since confidence interval is a two-tail notion, we have to use the two-tail critical. That comes out to be the region here. And we're saying 95% of all such intervals will capture the true difference, or the true increase for the regions involved. And that's the end of presentation 9.3. We ask you to review the results and go to presentation 9.4.